you very much for having me here. I know that the title is quite large, but if we understand the title, we will understand very good the presentation. So let me start. Or no? Okay. So, what we have. So I'm gonna present very quick what are spin boson system, what are tensor network, length. Then we are going to study and to show what is the X set and the boson model, and then the last part we are going to show some numerical results. So why spin bosons are important in physics? So they are the standard model for a lot of things in physics. For example, when we want to study the coherence or the noise in some quantum systems, so we need to understand this type of spin boson system. Also, this type of spin boson system have polarions that are very cool particles that appears in high energy physics. And with this type of spin boson model, we can understand some phenomena from, for example, quantum chromodynamics that, for example, the asymptotic freedom, we can try to understand this phenomena using this model. But this model, this spin boson system are very, very challenging to simulate. If we use exact models, exact methods like exact generalization or Lanzos method, we cannot go beyond a couple of spins. But luckily, this type of system lives in a tiny corner of the full figure space, in where the entanglement grows polynomial. So we can use tensor network to try to simulate the behavior of this spin boson system, and this is what we are going to do. Okay. So the natural representation in tensor network for a spin boson system is the matrix product state, in where the cost becomes polynomial, not exponential, and in where we can control the exponential cost of this simulation, controlling the bond dimension of phi of this spin boson system. In our special case, the physical degree of freedom not has the typical two dimensions of the spins, but have two n plus one, that is the product combination between the Hilbert spin space and the boson space. And the tool that we are going to use to simulate this type of system are going to be DMRD to find the ground state of the spin part, and TBDP to evolve this system to see what's happening in the real-time evolution. I'm not going to explain too much these two methods because are the basis in tensor network. So let me pass to the physical part. So our system of interest contains three main terms: the spin part of the Hamiltonian, the bosonic part of the Hamiltonian, and then we have a spin boson term that make the interaction between the spin part and the bosonic part. The goal is try to see if we have a quasiparticle that move along the spin chain, and this quasiparticle interact with the bosonic system through this spin boson term. What happened in the bosonic part of the Hamiltonian? So I'm gonna explain a little bit what is the boson-Hubbard model. Is the bosonic part of the system and contains three main terms. The first term is called the hopping term. P is the parameter that controls how easy it is for the boson to jump between sites. Then we have UV that represents the energy cost to have more than one boson, because here N represents the number of bosons per site. That represents the creation operator that creates one boson in the site I, and A is the destruction operator that destroys one boson in the site I. And then we have mu, that is the chemical potential that imposes the average occupation in the full system. So depending of the value of these three parameters, the behavior of the model is very, very different. We have in the phase diagram, we have a phase transition depending on these three values. And we know that at some specific values of these three different parameters, we will have something similar to a liquid. Okay. Okay. So this is a phase diagram of the Gaussian-Hubbard model. So we have two well-differentiated regions. In the colored regions, we have what is called the Mott insulator, in where we cannot add easily extra bosons because this costs energy, even if we change the mu, the chemical potential. And this is why it's called Mott insulator, because it's very, very gritty. Outside of this colored region, we have a superfluid phase in where the bosons can jump very easily, and the phase of the state is very sparse along the chain. So we are going to work in a mu over u value at 0.5, and we are going to change the other parameter p over u that controls how it is for the boson jump between inside. Okay, and in this phase diagram, K, that is the variation of the average occupation boson, when we change the chemical potential, is the parameter that controls the phase transition. So if we do some mathematical derivation and some approximation, we can go from the Gaussian-Hubbard model to another Hamiltonian that is a Hamiltonian that has the typical representation of a liquid, in where we pass from the discrete description to a continuous description. And now the variables, the important variables in this Hamiltonian are global and not individual, like in the previous one we have sites. No? Now here, rho is the density of fluctuation in one part of the chain, and chi represents the inverse of rho. And then we have theta, that is how change the phase between sides in a continuum system. So from this Hamiltonian, we can easily obtain the Lagrangian and obtain the equation of motion. We can obtain the wave equation of this system. So this is a semi-classical approximation. So we want to see if at some values of the Gaussian-Hubbard model we can obtain something similar to a liquid. So now we pass to the spin part that we have an X-set model. So I'm gonna present the quasiparticles in this model. The quasiparticle, one of the quasiparticles in this system is what is called a magnon, and where we have, if we have a polarized vacuum where all the spin are down, then the spin up represents a magnon that can move along the chain. We can also have two magnons that are coupled and move together, and this is called magnon-magnon or bound state in this system. So our goal will be construct this magnon-magnon state and move this quasiparticle along the system, and then see what's happening with when this quasiparticle interacts with the Gaussian-Hubbard model. So this is the Hamiltonian, the X-set Hamiltonian. So we have a first term that controls how this spin up and spin down can jump between sides, very similar to the first term of the bosonic of the Gaussian-Hubbard model, but now we have a spin, no, not we have boson. Then we have this capital delta that is the asymmetry that controls if we want to have two magnons that go together or not go together. So this delta imposes the stability of the magnon-magnon state, and then we have a single S set from individual sides, but in this case we are not to consider this term. So for us, this term is zero. So we start from the in the vacuum, all the spin are down. So in this system, the spin part not interact with the Gauss-Hubbard model, but only when we have a spin up, the system will interact with the Gauss-Hubbard model. Okay. So this is the theory about how to model this bound state with something that is called the answer. Is well known. So we are going to start creating two spin up. Then we are going to parameterize these two spin up using the center of mass and the relative position of these two spin up. And the wave function will have something similar to this, in where we have the exponential that contains the momentum. And then this A is a function that imposes the profile of the wave function. So we want an A in where the module of A is minus less than 1 to have an exponential decay outside of the region where we have this bound state. So also we need to select carefully the momentum of our quasiparticle, and now, as we know, with the beta answer, the dispersion relationship, we are going to select a momentum of pi half in where the particle not has a dispersion. So the second derivative of the energy is zero. We will have a very pointed particle that moves without dispersion. And this is the strategy using tensor network to construct the state of the spin part. We take the XX Hamiltonian, we impose that we want to have two spin up, and we add a trap to impose that we want the two spin up close. But to evolve the system, we keep the trap, and we select capital delta minus less than 0 because we want an stability of this bound state, and then with something called and these two first steps we use TMRD. Then we do a post-processing steps to add this momentum to the bound state. And then we evolve this spin system with TBDP. And then the last term of our system, this is the term that will do the interaction between the spin part and the bosonic part. So as you can see, we will have interaction between the two sectors only when we have a spin up. Okay. Then this NI mag measure the number of magnons, so this term will be non-zero and we only have the spin up. Okay. And now this is a summary. This is the full system, and this is why I introduce step by step, because if I introduce the full system, it's a little more. So now we are going to see the evolution of the quasi-particles interacting with the Gauss-Hubbard model, and we will see what's happening. So the first thing that I want to show is in the left plot we have the evolution of the quasi-particle. As you can see, we have a very pointed quasi-particle that evolves in time, and the system size is 80. 80 sides, a chain of 80 sides. And we can see how changes the behavior of the quasi-particle when we increase the value of lambda, that is the term that imposes the interaction between the spin part and the bosonic part. So as you can see in the top plot, we can see a very, very nice quasi-particle, but when we increase the value of lambda, the interaction becomes more strong, and we have some dispersion due to this interaction. In the left plot, we have the relative change in the size of the quasi-particle. So this measures the dispersion of the quasi-particle depending on these two values, lambda and P over U in the Gauss-Hubbard. So in the superfluid phase, we have less dispersion. Then this is the main plot for the presentation. We have four columns. The first two columns show the evolution of the spin part, but also the bosonic part. Here we can see the excitation of the Bosa-Hubbard. So we can see how we create bosons in the part where we have the spin quasi-particle, and this is what is called polar, where we have a new particle that is the spin quasi-particle plus the cloud of bosons around the spin the spin quasi-particle. And in the first two columns, we have an evolution of the spin part with the bosonic in the regime in where we have the mod regime. So we don't have some propagation like an aerodynamical propagation. But in the second plot, we have with the same values of lambda, we have clearly a wave propagation in the bosonic part due to the interaction with the spin part. So what we do is we measure the speed of this wave cone, and we check it with the prediction. So we see that when we increase E over U, when we are in the superfluid regime, the prediction matches better with the numerical simulation. Also, in this subplot, we can see the asymmetry between the speed of the left part of the cone and the right part of the cone. So we see that at the same time that the result increase the match, we see also how the asymmetry decreases, because we should see a perfectly symmetric wave propagation between left and right part. Well, this is the same plot, but in this case, in the superfluid regime, and only we change the value of lambda, so we see the same qualitative behavior. The only thing is that the excitation in the bosonic part increases, but we don't see any behavior beyond this qualitative semi-classical description. And the last plot is the TBDP simulation and the predicted behavior in simulating the wave, the equation of motion using Rumpel-Hubbard, and we see that qualitative we see the same behavior. So we have a microscopic proof of hydrodynamics in this model. We have a quantitative arrangement, and with this tensor network approach, we can explain the simulation. Thank you.
Question. So thanks a lot for the interesting presentation.
Thank you.
I have a question on one. I think the second exactly. No. Exactly. No. Go back. Exactly.
Okay.
I look at the last plot in the bottom to the right. I see the cone. Exactly. There is the cone which is emitted at the speed of sound.
Yeah.
With the red and blue stripes, which basically go parallel.
Yeah.
And in the center, there is a trace of a polaron.
Correct. Yes.
So, is it correct?
Yeah.
So, do you see any renormalization of the properties of motion of the spin impurity?
Yeah. I have this problem. I don't know. Yeah, and this is well known how change the mass and the speed of this type of quasi-particle when you change the interaction between the spin part and the bosonic part. So basically, the quasi-particle becomes more slower because the quasi-particle has more mass. Basically, yeah. But it's nice. Yeah. You see the same polaron structure, but you see this waveform.
No, yes, but the polaron is more.
Yeah, the polaron is this.
Exactly. Yes.
Maybe I shall.
Okay, here is more visible.
Yeah.
Exactly.
Yeah.
Another question back. Can you elaborate on this box that you compare to Rumpel-Hubbard? Like, what are you doing to do Rumpel-Hubbard?
Well, I take this equation, I take the same values of this equation and I compare. Yeah.
Have you thought about an experimental system in which this kind of model is,
Yes, this is so as you can see in the first slide, I am from Kilimanjaro, so we are a quantum company in Barcelona, and we make quantum computers. So this type of experiment are nice experiments, right, to simulate in quantum computer.